So hello everyone, I'm Tong Wu. So in this video, I would like to show you how to use MAN, Modal Analyze of a Resonator, which is an open source software written in MATLAB and devoted to the analysis of electromagnetic resonator in the base of resonance modes. So for any technical problem with this software, please feel free to contact me with the email. At the beginning, I would like to first give an overview of the software. So MAN combines the two first software packages, QM-PO and QM-Add, which are respectively launched in 2013 and 2018. So these packages compute and normalize the QMs of virtually any electromagnetic resonators, be they periodic, non-periodic, dispersive or non-dispersive, isotropic or anisotropic. They also compute many important figures of merit of the QMs, such as their quality factor and mode volumes. In addition, the MAN software also features a lot of toolboxes. So these toolboxes can be classified into two types. The first kind of toolboxes is used to compute some other intrinsic properties of quasi-normal modes, such as their multiple components, far-field radiation diagrams. The second kind of toolboxes are used for analyzing various embolic resonators with a superposition of their quasi-normal modes. Therein, providing a transparent interpretation of the physics of these resonators. So these toolboxes include, for example, a reconstruction of the scattered field, the extinction and absorption cross-sections, the Purcell factors as a sum of quasi-normal modes. So for downloading, please check the website of the software in the Zenodo website or the website of the group. So the software will be updated from time to time to fix some errors, as well as incorporating some new features, new functions, and some new toolboxes. So please be sure what you're going to have is the latest version before downloading. Once you have unzipped the package, you can find the following folders and files. So in the tutorial folder, we have provided a lot of MATLAB scripts illustrating how one compute, normalize, sort, and save the quasi-normal modes using the QM solvers, QM-PO, and QM-Add. So they basically the scripts in these folders are the scripts which you should run first to learn how to compute the quasi-normal modes and how to normalize it. And in the toolbox folder, we have a lot of toolboxes. Basically contain the toolboxes in MAN. So for most of the toolboxes, we have provided a user guide and some MATLAB codes giving some embolic examples illustrating the functions of the toolboxes. And in the solver folder, we have the MATLAB functions, which are used by the script in the tutorial folder and the toolboxes folder. So in general, we do not recommend the user to change any of the program inside this folder, as they may cause some error of the program in the folder of tutorial or the folder of toolboxes. So in the MAN models folder, we have more than 30 COMSOL models, which are used by the two QM solvers, QM-PO and QM-Add, for computing the quasi-normal modes. You can check the geometry and material parameters of your concerned system by clicking these models. In addition to the folders, we have provided also 3 documents which illustrate the capability of the software and show the procedure how to use the man software, and also list some other technical details. You can click the repertoire of available models of QM-Egg and QM-PO document to check all the existing models that have been considered in this software. So we understand that once you get a new software, you would always like to do some test running before going into details. So therefore, in the README first document of the MAN software, we have provided some procedures, and following which the user can rapidly do some calculations themselves. And by doing so, they can be readily be familiar with the software and have a first impression of the capability of the software. And in addition to the README first and the repertoire, of course, we also provided the user guide of the software, which gives you basically all the details of this MAN software, including the mathematical background of the 2 solvers, QM-PO and QM-X, and some introductions of all the toolboxes included in the software, and technical details about how to build the CAMSO models to compute the quasi-normal modes, such as how to define the wake form, how to define the permittivity of your resonators, and so on. So to use the MIND software, please make sure that the MATLAB in your computer is a version no earlier than 2019. B, because we cannot guarantee that it can be run with a too old version of MATLAB. So the installation of the MIND is fairly easy. First, set your current folder of MATLAB as the main director of the unzipped man software, and then run this add man path function in the root folder. So this function will add the paths of all the main directors, as well as the paths of all the sub directors of the man software to your MATLAB path. So for studying advanced geometries, one need to start COMSOL multiphysics with MATLAB. The MAN models folder, as I mentioned before, it contains more than 30 COMSOL models, which had the .mph files. So these models were built with COMSOL version 6.0. So users running older versions of COMSOL may have trouble in opening and loading these models. To avoid this problem, they may simply run the build and save COMSOL models.m file inside the tutorial folder. So this function will automatically remove all the existing COMSOL models inside the man models folder and replace them with models which are compatible with your version of COMSOL. In the following slides, I will give you some simple examples showing how to use the 2 QM solvers, QM-Egg and QM-PO, to compute and normalize the quasi-normal modes of the resonators. The first example, I would like to show you how to compute the quasi-normal modes of a very simple resonator, a 1D Fabry-Pérot resonator. So this simple example is basically a dielectric slab with a permittivity of 3.3 and length of 1000 nanometer and embedded in an air background. So inside the slide, the quasi-normal mode fields of such a system is composed of counter-propagating plane waves, whereas outside the slide, the quasi-normal mode fields are outgoing plane waves. You can find the analytical expression of the quasi-normal modes of such a system in many references, including this one published in 2018. For this simple example, the user can readily learn the algorithm adopted by one of the QM solver in our software, the QM pole solver. It also illustrates how does the MAN software help the user to identify which are the QMs, quasi-normal modes, which dominate the response of any given optical resonator. The source code of this simple example can be found in the common folder under the tutorial folder of the software. So this source code used the QM pole solver to find the quasi-normal mode of the 1D Faber-Pehot resonator, and it can be run independently with console. So please see the paper published in 2013 for any detail about the algorithm. In the user-defined section of this script, the user can find the following important parameters to control the iteration calculation of the QM pole solver. The guessed wavelength defines the initial frequency of the iteration. It is recommended to set it as a value within your concerned spectrum range. And you can set multiple guessed wavelengths, and then the code will find you an equal number of quasi-normal modes. In the source code, you can also define the iteration number. In general, the precision of the algorithm will increase with the increase of the iteration number. However, we do not recommend the user to set the iteration number to be a very large value in order to avoid the numerical instability issue. At last, you can also define the test point. As the increase of the iteration numbers, the frequency becomes more and more closer to the pole or the QEM eigenfrequency of your system. The field at your defined test point will become divergent. And in general, if your calculation is accurate, the computed eigenfrequency and eigenvector of a quasi-normal mode should be independent with your test point. Since as the frequency approaches to the pole, the every coordinates of your system, the field at every coordinates of your system will diverge at the same rate. However, in general, we do not recommend the user to put the test point to be very close to the source, which is used to excite your system to avoid some numerical issue. So here I would like to show some results of computation. The first figure returned by the program consists of 3 panels. The panel on the left shows the field at the test point as a function of the iteration number. So as shown in the figure, for a correct computation, the field at the final iteration should be several orders of magnitude larger compared to the first iteration. The other 2 panels show the real and imaginary parts of the frequency. And if your computation is accurate, this value should be stabilized in the last several times of iterations. And you may have noticed red points in the panels of frequencies. This point is a frequency which has the closest distance with the QM pole in the complex frequency plane. And it is deduced from the frequencies and the test fields of the last 3 times of iterations. With this frequency, along with the frequency and the field computed from the last time of iteration, we are able to compute the normalized quasi-normal mode of the system from the formula which I have shown here. The program also returns the complex eigenfrequencies of the QEMs. Here I have provided 7 guessed eigenfrequencies in the input section. Therefore, you can find 7 quasi-normal modes that have been found by the solvers. By clicking the eigenfrequencies, you can find some important information of the quasi-normal modes, including the quality factor, the mode ratio, and the excitation strings. The excitation strings, which is described by the size of these circles, which qualitatively describe how much the mode can be excited by a plane wave. For example, for a mode with large circle, it's more likely to be excited when you shine the system with a plane wave, whereas for these modes located in the center of this complex plane, they have small circles and they are likely to be excited. Besides that, we also define the mode ratio, which is represented by the color of the mode, varying from yellow to blue. For a quasi-normal mode like, it has a color of yellow, whereas for a PML-like mode, it has a color of blue. Here in this system, since we rely on a trivial Maxwell solver, which does not implement any PML layers for computing the QM of the system, all the modes are quasi-normal modes. Therefore, here in this figure, you can find that the color of all the modes are yellow. And finally, after the computation of the modes, the user can define coordinates to plot the fields of the normalized quasi-normal modes. For example, here in this example, I have selected the mode number 1 to plot its normalized field and the mode volume. At last, I would like to stress that in this simple example, we rely on the very trivial Maxwell solver that only can compute the field scattered by a 1D slab excited by a planar source. So quite simply, this trivial 1D Maxwell solver or toy Maxwell solver can be replaced by other frequency domain 2D or 3D Maxwell solver, such as the ANSYS Lumerical or CST Studio. So in that way, the user can deal with a more complicated structure. For example, a structure with arbitrary shape or materials. So what the user only need to do is to basically, in order to incorporate this Maxwell solver, they only need to modify this spooling to interfaces functions. So one interface function is this mFun function, which basically drives the frequency domain Maxwell solver. In our case, is this toy Maxwell solver to compute the scattered field at a complex frequency. And the other interface function is this post-processing function, which is able to return the scattered field in any arbitrary given coordinates based on the result computed by that mFun function before. And for users of COMSOL, life is much more easier. As you can check in the man models folder, we have provided more than 30 predefined models, including photonic crystal cavities, plasmonic nanospheres, nanoparticle on mirror systems. So these structures basically cover all types of systems that you can come across in the area of nanophotonics. And we further also plan to increase the number of models over time. Therefore, the users are encouraged to build their own models by modifying these existing ones. So to learn how these models are built, please check the detail given in the My User Guide in the root folder. In the following, I would like to show how to use these COMSOL models and along with our MATLAB codes in the MAN software for computing and visualizing the quasi-normal modes. Let us discuss the simple example provided in tutorial 2D.m program. In this simple example, we would like to compute the quasi-normal modes of a coupled wire of 2D silicon nanowire on substrate, as shown in the figure. Here by 2D, what I mean is that the electric field is invariant along the longitude direction of this silicon nanowire. The material of the nanowires is highly dispersive. Therefore, it is difficult to be handled with a conventional linear eigenfrequency solver, such as the eigenfrequency solver of the radiation frequency module in COMSOL. In the band models folder, there are two types of models. Models beginning by QM-egg and QM-PO are used with the QM-egg and QM-PO solvers, respectively. Therefore, in this specific coupled nanowire example, you should use the MAN model QM-egg 2D silicon wire TM if you would like to use the QM-egg solver to compute the resonance mode of the system. And if you would like to use the QM-PO solver, you should otherwise select the model QM-PO to the silicon wire TM model. Let us show how to compute the quasi-normal modes of this coupled nanowire example with the QM-egg solver. In this example, what you only need to do is to simply open the COMSOL file and the QM-egg to the silicon wire tm.mph file. In the setting menu of the eigenfrequencies, you may define the desired number of eigenfrequencies, and then the solver will return a number of QM, which is about 2 times about the value assigned by the user. And the user also needs to assign a value for the solver to set the eigenfrequency around. Please be sure this value is located in the spectral range of your which you are concerned about. So once you have set this value, please click the compute button, and the solver will start to look for all the QMs for you. After the computation, you may visualize the quasi-normal mode fields using the post-processing module of COMSOL. And the normalized quasi-normal mode of the system is given by the QM field computed by CAMSO divided by the square root of this factor Qn, where the Qn is the normalization factor, of which definition can be found in our archive paper. So in general, there are two kinds of modes that can be found. The first kind of modes, we call them the quasi-normal modes. The fields of these modes are mainly concentrated in the vicinity of the resonator and have vanishing field inside the perfectly matched layer. And these modes are the eigenfrequencies or the field distributions of this mode are in general not influenced by the parameters of your perfectly matched layer. For example, when you change the thickness of a perfectly matched layer a little bit, what you will find that the field distribution or the eigenfrequency of this mode are unchanged. The second kind of modes, on the contrary, have large field inside the perfectly matched layer, and their eigenfrequency and mode profile, on the contrary, are very sensitive to your perfectly matched layer variation. And if you change the thickness of your perfectly matched layer, you will see that the eigenfrequency of this mode will shift a lot. We therefore call this mode a perfectly matched layer. And physically, this perfectly matched layer originates from the finite size perfectly matched layer and replace the continuous spectrum of the optical operator from the coupling with the open space. In general, the user would like to distinguish these two kinds of modes, the QAMs and the perfectly matched layer. And this is because that for most of the system, the main feature of your optical response of your optical spectrum is only dominated by the QAMs, and the perfectly matched layer only gives you a featureless or a flat contribution to your optical spectrum, which therefore is less interested. However, to distinguish these two kinds of modes is always a very tedious job, especially when you have computed a large number of modes. And in the MATLAB script, which I will mention below, we have developed a function which exactly helps the user to do this distinguishing between quasi-normal modes and PMR modes. Alternatively, the user may run the tutorial 2D under the tutorial common folder to compute the quasi-normal mode of the system with the QMX over. And by default, this tutorial 2D program drives the .mph field I mentioned before to compute the QM fields. It offers a lot of built-in functions, which allows user to explore the quasi-normal mode fields in any user-defined coordinates. In addition, it features also features a set of built-in functions that provide some direct access to some important quasi-normal mode figures of merit, such as mode volume, quality factor, excitation strength, and so on. It also helps us to do the tedious task, which I mentioned before, which is to identify the QM modes and the PMR modes. Usually, the QM computation will consume most of the computer time, and this is especially true when you're dealing with some optical resonator in three-dimensional. The user may save So in that case, the user should save the result in the data side of their console field by using the save model function. And the QMs will be, so when the next time you use this to tutorial your 2D or 3D function, the QMs will be loaded instead of being recomputed. So here I would like to show some results returned by the tutorial 2D program. Like the 1D example I mentioned before, the eigenfrequencies of the computed quasi-normal modes are shown in a complex frequency plane. Specifically, we have computed the mode ratio, which tells you whether the mode is more quasi-normal mode-like or PML-like. And for the mode with for this mode with yellow color, this big circle, basically you can find from their field distribution, that the electric field is mainly concentrated inside and in the vicinity of the resonator, and the field inside the perfectly matched layer is vanishing. And on the other hand, for this greenish mode, you find that basically their field distribution inside the resonator is very small, whereas it has a large field components inside the perfectly matched layer. And therefore, they represent this mode with a green color, and it can be attributed to a PML mode. Also, same with the 1D program I mentioned before. This tutorial 2D also allows user to define coordinates to plot some important values. For example, here I have defined coordinates to plot the permittivity and the mode volume of the quasi-normal mode. In the slides before, I have shown how to compute the quasi-normal modes with the QMX solver. Now I would like to show how to compute it with the QM pole solver. The building of the model used by the QM pole solver is pretty easy, as they are very similar to the COMSOL models used for, as these models are very similar to the COMSOL model used for simulating the scattered field at a real frequency. The only thing one needs to be care about is that the material inside of this model should be built as a function of the angular frequency. And unlike the models used by the QMAC, these COMSOL models cannot be run alone, and you basically need a MATLAB script to drive this COMSOL to implement the iteration algorithm for finding the eigenfrequency. For example, you can use the tutorial 2D program, which I have mentioned before.
So to use the QM pole solver for compute the quasi-normal modes of this 2D resonator is pretty easy. Basically, what you only need to do is here in this tutorial 2D program, here you change the man solver from the QM egg to the QM pole, and you select the corresponding model of the QM pole solver. And after doing this, you run the program and wait the results to come.
So here I show some results returned by this tutorial 2D program when we use the QM pole solver for solving this two-coupled nanowire system. And like the 1D example I mentioned before, on the left-hand side, you can see the electric field at the test point as a function of iteration. And for an accurate calculation, the electric field at the final time of iteration should be several orders of magnitude larger compared to the initial iteration, compared to the result of the initial iteration. And on the right-handed side of this figure, we have the frequency for each time of iteration. And for a correct calculation, basically you will find that the real and imaginary part of the pole or the frequency should be stabilized and approach to the value of the eigenfrequency of your quasi-normal mode. Like the QMX solver, the QM pole solver also returns the eigenfrequency of the computed QM, and they are displayed in a complex plane where you can click the eigenfrequency of each QM and to check their important information such as eigenfrequency, quality factor, mode ratio, or the excitation strength. And by comparing the results obtained from the quasi-normal mode X solver, what you will find that is these two solver basically find the exactly same quasi-normal mode. You may be a little bit curious about why the mode ratio or the excitation strengths for these two obtained from these two solvers are different. However, in general, you don't need to be too worried about that because this mode ratio or the excitation strengths are only are not physical values. They are only values defined by ourselves to characterize whether the mode can be well excited by a plane wave or to tell whether they are quasi-normal mode-like mode or the PML-like modes. And the definition of these two values for the QMX solver is different from the QM pole solver. And that explains why the values returned by these two solvers are different. And for the exact definition of this mode ratio and the excitation strength, you can refer to our reference of this archive paper. Besides the QM pole solver and QMX solvers mentioned above, man also provided lots of toolboxes for reconstructing the response of the system, such as the field scattered by the resonator, the extinction or absorption cross sections, or the Purcell factors as a superposition of the quasi-normal modes. There are also several toolboxes provided which can be used for to compute some intrinsic properties of quasi-normal modes, such as toolboxes for computing the multiple components or the far-field radiation diagrams. I have listed the toolboxes of the version 8 of the software. And each toolboxes can be found in a separated folder, as you can see from this figure. Which for each of the toolboxes, it's in general composed of a user guide document and several dedicated examples. And some toolboxes also contains a source code folder, which contains a lot of MATLAB functions, which are used explicitly by the toolbox. The examples of the toolboxes are usually self-explained and can be run step by step. You can readily learn the capability or the function of the toolbox by running these dedicated examples. Toolboxes are developed for different applications. Their logic of running is basically the same. So in general, the MATLAB program in these toolboxes first drive console to compute the quasi-normal modes. Or alternatively, this program load information of the QEMs from the already computed .mph field in the man models folder of the software. And then use this important information of the QEM and the quantity defined by the users. We can compute some results of interest. We hope that in the future, these two boxes, along with our two QM solvers, QM Pole and QM Egg, will inspire the users to develop new toolboxes dedicated for their own applications.